Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
So where do all these equations, these physicsy kinematics equations come from? Well, that's what we're going to talk about in this segment. Because it's actually relatively simple math and kind of cool, actually. Well, it turns out it all starts with the graph. If we have a graph that looks like this, there's something that matters when we look at it. It's got a slope. So it's velocity versus time. Let's get this through here. Then what's the slope of that line? The slope, of course, what is slope? Let's review. Slope is the rise over the run, or delta y over delta x. But in our case, the slope means something. So we have acceleration is equal to delta v over delta t. But we could also write that as what? We can say A is equal to v2 minus v1. That's with a change in, right? Divided by t2 minus t1. You see how this is working? And folks, what we can then do is, or we could just say this. We can say A is equal to v2 minus v1 over delta t. Very often, because the change in time is, it's not a vector, we don't necessarily need to do the v2 minus v1. We can then just rearrange this. If we rearrange this, we can say if we rearrange this, we can A times delta t, right? I'm multiplying across here, is equal to v2 minus v1. Hopefully you're seeing what this is. But more commonly, what we do is we solve for v2, and we get v2 equal to v1 plus a delta t. Now let's put it appropriate. These are now vectors. This is equation 1 right here. Now make a note here, you want to have consistent units. This will need to be in meters per second, as is this. But this, of course, will be meters per second squared, and this one will be in seconds. Or you can do kilometers per hour, but that'll make it a lot easier. So that's relatively simple how we derive, if you will, equation number 1 down here. Let's talk about how you would derive equation 2. Again, we're going to have sort of the same kind of a deal. We're going to have a graph. It comes back to the graph. So let's have a graph right here. But now what I'm going to do, so this is, V1, and this is V2, and this is T1, and this is T2. Now, this is an interesting one because we learned something a bit ago in a previous segment. We said that the area underneath the curve, so to speak, is equal to what? It's the displacement. So you might think of it this way. This is area 1, and this is area 2. So we can see that the total displacement would be equal to area 1 plus area 2. Now area 2 is going to be what? Let's think about this. It's going to be, well, let's do that. Area 1 is, well, do area 1, I guess. It's going to be T2 minus T1. That's the base of the triangle, right? Times V2 minus V1 divided by 2, because length times width divided by 2, base times height, right? Okay. And A2 is going to be, let's call that, it's just delta t, if you will, because that's T1 minus T2 times V1, right? And then we simply add these together. We add them all together. And what we end up with is, we can say the delta D, that's the A1 plus the A2, is equal to delta T times V1, right? That's what we got here, plus 1/2 times delta T times V2 minus V1. Make sense? But we rearrange this. Equals, pardon me. We can rearrange this, and we usually do it this way. We just say delta D is equal to V1 delta T plus 1/2, okay, times delta T times delta V. And now we have our equation. Actually, we probably oversimplify it. We're going to simplify it this way. We can also say delta D is equal to V1 delta T. No, pardon me. We rearrange this, we say delta D. We just rearrange. We do some simplification of the fractions. You can say 1/2 times V1 plus V2 times delta T. And that's the equation. This is equation number 2 right here, and you can see how it's derived. So let's now take a look at equations 3, 4, and 5. Now the key thing about these is they're actually derivations of the first equation. So let's do number 3. What you're going to do is start with those two equations. So they are, if you recall, so what we do is we know that this is V2, and we can take this V2 and substitute it into here. So we can say delta D is equal to 1/2 times V1 plus V1 plus A delta T. See, I've just substituted here times delta T. And now we're going to simplify this expression. So these parentheses, this is all plus, they go away right here, this and this. So we'll have 1/2 times 2V1 plus A delta T, still times delta T, all right? And then what I get is I want to solve, let me think how to do this. I'll distribute, so I can say I'll take the 1/2. So 1/2 times 2, okay, is 1. So I can say V1 plus 1/2 A delta T, and that's all times delta T. Now the delta T now can be distributed into the fraction, so I can say V1 delta T plus 1/2 A delta T squared. So delta T, this is delta D. So you're just simply plugging in equation 1 into equation 2, and this is equation number 3. All right, what about equation number 4? Again, you're going to start with the same two equations. So in this case, what I'm going to do is I'm going to rearrange equation number 1, and I'm going to solve for V1. All right, I'm going to rearrange this. So I can rearrange this, subtract V1 from both sides. Actually, no, I subtract A delta T from both sides. I can say V1 is equal to V2 minus A delta T. Now I have a V1, and I can plug this, if you will, into the second equation. So I can say delta D equals to 1/2 times, now V1 is this, V2 minus A delta T, all right, plus V2 all times delta T. Okay? And so let's distribute, let's see, we got a V2 and a V2. I got 2 V2. So we can say 2 V2 minus AT, and that's still times 1/2 times delta T. I multiply the 1/2 in there, so I can say V2 minus 1/2 AT, and that's times delta T. And then I can say V2 minus delta T times V2 equal minus 1/2 AT squared, or delta T squared. And that's, of course, equal to delta D, and that's equation number 4. So in this one, we want to solve for time. So time is the variable. So what we're going to do is we're going to solve for t from this equation and then plug it into this equation. So if I rearrange and solve for t, I could subtract V1 from both sides. So I can say V2 minus V1 is equal to A delta T. If I divide both sides by A, then I can say that delta T is equal to V2 minus V1 divided by A. Now, this is delta T. We're going to plug that into the equation over here, right? So I can say delta D, so boom, here, right, is equal to 1/2 times V1 plus V2 times delta T, which is V2 minus V1 over A. Now this gets a little bit complex. It's not terrible to do this. So let's see if we can figure this out. So this is you can also move this half and just say 2a here. All right, we're still trying to solve for delta D. Mr. Bergmann got lost here. So if I carry this out, so I've got V1. All right, let's do this here. So this is like remember this is from algebra. So I can say V1, V2, okay, minus V1 squared, right? That's this times this. And I can take, plus V2 squared. And then I can say, oops, hello. And this is going to be plus negative V1, V2. Now, if you notice this, I'm just trying to simplify this piece right here. V1, V2 minus V1, V2, these cancel out, right? So it'll be, and I'm going to rearrange this. I'll say V2 squared minus V1 squared over 2a equals delta D. And then we can simplify, and we can take cross multiply. We can say 2a delta D, multiply both sides by 2a. 2a's cancel. Now, what we typically do is we just say we solve for v2. So I want to get this. I would add then v1 squared to both sides. And I can say v2 squared is equal to v1 squared plus 2a delta D. And that's equation number 5. We've eliminated time, and now we have the last of our 5 equations. Now you might ask, why is that important? It's important to know that it all comes back down to a very simple understanding of this graph. If you can understand this graph right here, by just understanding that the total displacement, all right, is the total, or the total area of the curve is the displacement, and then you solve for just simple equations, you can come up with these 5 equations, and we can solve this problem, and it's going to help us out in all of our physics problems. So just know that there's a grounding in where it comes from, and this will help you as you're solving the more difficult problems as we go forward. You guys are awesome. We'll see you in class.
Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.